Hello, this is lecture 18. Today we're doing simple linear regression. You have a quiz on Thursday on ANOVA and the Bonferroni test. I should mention that there is no take-home portion of the final, as that I was able to reserve our room for a 3-hour final on Wednesday from 9 to 12. And I'll be giving you more information about the final soon. So chapter 14 is about linear regression, and it makes sense to also discuss multiple linear regression, not just simple regression. So we often often it's convenient to assume that we have a linear relationship between some response variable and some predictor variables. It's important to know that here we assume that our response variable is normal and our predictor variables are independent normals. And we have n observations for each of these. Usually your data doesn't actually fit on a line or a plane. You have a scatter, right? So you have some noise, and we write E1 to En to be these noise terms or error terms, and these are independent normal 0 sigma squared. We say that these error terms are homoscedastic, meaning that these error terms, the variance, the sigma squared, has no dependence on x. It's just a constant. So let's introduce just some matrix notation here. So we have a n by 1 matrix for y, x0, x1 out to xk. So we have k predictors here. And beta is a column vector. We have k plus 1 coefficients for our linear plane. So these are constants we're going to need to estimate. So these are our parameters, and we also have some error. So let's call X our design matrix. X is a n by k plus 1 matrix with column vectors x0 out to xk, where n is greater than or equal to k plus 1. We're going to assume that X has full rank, which means that these column vectors are all independent, and it allows us to invert X transpose X. I write X transpose as X with a tick mark. So our standard statistical model is Y is X beta plus E. E is homoscedastic, meaning that the errors have no dependence on X. There's just a constant error. And writing out what all these matrices are, here we get these we get basically n equations, right? So each row here is a different observation, and we have one response variable, y, and k predictor variables, x. So, of course, k is 1 is the simple standard statistical model. So let's just take a look at the case where k is 1 and n is 3. So this we can easily draw. Here, for example, it's fair to assume that we have a linear relationship between x is father's heights and y is son heights. And so we have this equation, y is beta 0 plus beta 1 x plus some e here. So it's important to emphasize here that beta 0 and beta 1 are unknown parameters. and x is some const is our data, so that's fixed. Our e is a random variable, and hence our y is a random variable. So I've plotted here our 3 points, our 3 pairs, x1, y1, x2, y2, x3, y3. And so we have 2 lines. There's a Tyche line and a regression line. So the Tyche line is actually not known. So, because we don't know what beta 0 and beta 1 are. So this Tyche line is not something we know. It is in some sense the true relationship between our variable x and y. But what we are able to determine is the regression line, which is the best fitting line through our data. And what we mean by best fitting we'll talk about in a moment. But notice here I've indicated E1, E2, E3. These are the errors from our data to the Tyche line, and E1 hat, E2 hat, E3 hat, these are the residuals. These are the errors from our data to the regression line. Okay, and so an important assumption here is that our x and y are related by a linear model, and so essentially the points should be a random scattering around the Tyche line, and so we would then expect the regression line should be pretty close to the Tyche line, and so we should essentially be getting a random scattering around the regression line, and so the residuals should also be homoscedastic, and so just a constant variance. And so it's common to check that. So you make a residual plot, and your residual plot, as I've shown here, should look like the good that I've written here, not the bad, where you can see sort of a fanning out, for example. You have different variants for different I. Who is Tyche? Tyche is the goddess of fortune, and Tyche knows what beta 0 and beta 1 are. There are different versions of Tyche depending on your preference. So now, what we want to do is we want to find the best fitting line through our data. So the best fitting line means the line that minimizes the sum of the residuals squared. And another way to say that is that it minimizes the Euclidean norm of the vector of residuals. So just a little bit of background about what the Euclidean norm is. And now there are 2 ways to estimate beta. We call the estimate of beta beta hat. One way is with calculus, and another way is geometrically. So we'll start with the geometric version, since it's so easy and it really applies to the multi-dimensional case just as easily as the simple case. So we have y, a vector in Rn, and we have the columns spanned by x. So x, our design matrix, has k plus 1 columns, and they span a subspace of Rn. Since so x has full rank, and so I've sort of drawn a picture of that here. And what we want is we want to find beta hat here such that we have 2 vectors. We have y and we have x beta hat. x beta hat lives in the column space of x, right? So beta hat is just, beta hat you can just think of it as a linear combination of columns of x. So it lives in the column space, and so the difference between y and x beta hat, that is y minus x beta hat, that's exactly the vector of residuals, and we want that vector of residuals in some sense, right, to have minimal Euclidean norm. So to minimize the Euclidean norm of y minus x beta hat, we take an orthogonal projection onto the column space, which, right, so the shortest distance from y to the plane is an orthogonal projection, and so this orthogonal projection should be perpendicular to any column vector in our column space. And so what that means is that the dot product of x with our vector y minus x beta hat should be 0. And that just amounts to, if you solve for that equation, you get that beta hat is x transpose x inverse x transpose y. So this is a famous equation, and it's easy to remember. So I should just also mention that what happens if y actually lives in the column space. In that case, this distant, the Euclidean norm here is 0, so y is x beta hat, which is just to say that we have a perfect fit of our regression line to our data. There's no residuals. So let's see actually what this strange looking beta hat formula is for the simple regression case. So we'll show that beta 1 hat is the covariance of xy over the variance of x, and that beta 0 hat is essentially the mean of y minus beta 1 hat, the mean of x. And so to easily talk about this, just imagine that x in this case is a uniform random variable on x1 to xn, and y is a uniform random variable on y1 to yn. So all these points are equally likely. So the expectation of x is just x bar, the expectation of y is y bar. The variance of x and the covariance of xy are just the familiar formulas for variance and covariance. So then, just following the book here, we can actually write out what x transpose x is, and take its inverse and multiply it by x transpose y. And wow, this is just so awesome. Look at this formula here. So this formula is a little bit hard to digest, so it's good to just recognize what these pieces are, and it's easy to see that beta 1 hat is the covariance of xy over the variance of x, and not with a little bit of trickery here, it's easy to show that beta 0 hat is y bar minus beta 1 hat x bar.